Hello class. This video is designed for Probability Math 331 and we're using the Ugarte, Militino, and Arnholt text. This is page 80, as you can see, and this may be the first one of these we're doing, I'm not sure. I'm being a little experimental here. But the goal of this is to be a companion to your reading of the text. Okay, so I'm not going to do everything, but I'm going to kind of walk through some parts. So I believe the best way to do it is going to be to read the passage and then pause and take the read and then unpause and just kind of follow along. You may go over things several times. There's some definitions here. I think the text in itself is relatively well written. So we've been relying upon that this semester, no exception here. But as it gets a little trickier, we're moving in. Set theory, this should be review. So we want to take note, we have the commutative laws for union. And as you typically read, you should be with pen and paper or pencil and paper in hand and diagramming out the different pieces. So E union F, I've got E here, I've got F here. Union is going to be both sets, so I'm just kind of sketching out here. Since I'm including both, then everything shaded is my union. Now intersection is this symbol, so that's going to be only the thatched region. So just sketching the diagram as we go. You could set up a simple example if it helps. We're going to read every single example in the text. Very important. Okay. So let's see. Associative laws. All right, again, we want to go through these. I've got some sketches drawn out here, but you want to do each one and convince yourself. So in the parentheses, we're associating. You got E union F, then G, or F union G first, then E. And so in my first diagram here, we've got E union F. That's not it. E union F. Okay, that's going to be both regions, so I'm just going to go whole shaded here. Kind of the whole region there. EF, and then union G, so we'll go union G. And of course, let's just use a different color. It's kind of obvious, but it's everything. So that's the whole thing. Now conversely, if you go FG, then you're going to get these two full circles, union E, we get the whole thing. Intersection is not as simple, and I have that one over here on the right. Okay, distributive laws. Again, we're going to take E intersect F, union G. So the way it works is E unions with the G, and then F unions with the G, and we intersect those two parts here. So again, check the diagrams, make sure you buy it. We will eventually move into actually doing some of the notation algebraically. Okay, De Morgan's laws, same thing. All right. Let's see. So yeah, just think it through. Make sure you're tracking here. All right. So let's go on to interpreting probability. There may be some simple things about this. You're like, yeah, you just get it, move on. But I would urge you to resist that temptation and try to grasp the nuances now, because it will lay a more solid and wide foundation for later when you're really going to need it. Okay, now first off is an intuitive approach to probability. It says, suppose an experiment can be performed n times under the same conditions with sample space omega, and we're going to typically use that as our sample space symbol. So that's going to be our big box. Let n of e, little n of e, denote the number of times in n experiments that the event e occurs. Okay, so here is e. All right, so I'm just going to put an e in here, and this guy's big omega. Whoa, big omega. All right, relative frequency approach to probability, something that we'll refer to, defines the probability of event E as follows. Okay, so we're going to take n of E, that's the number of ways for event E to occur, divided by, they're putting a little n. You could just as well put n of omega if you wanted to think about it that way. That's the total number of elements in the sample space, and that's fine. N of omega right here. Okay, either way, what you have is number of events E over n of omega, and if we have processes that are not fixed, in other words, they could be repeated over and over, then we'll think of a limit as n goes to infinity. If it's finite, let's say it's just the number of outcomes on a die, and we consider 1, 2, 3, 4, 5, 6, then number of ways to get the 1 over the 6 possibilities would just be 1 over 6, or number of ways to get the 3 out of 6 or whatever. So there's a bridge between what's empirical, can just be repeated over and over, and what's theoretical, where you can think of your total possible number of outcomes as fixed. Okay, at any rate, this is useful, but it's not a firm enough theoretical foundation. And so a Russian mathematician by the name of Kolmogorov came up with the following axioms for a probability. And so we're going to look at these 3 axioms. Like in geometry, we've got our 5 axioms for Euclidean geometry. Same thing here in probability. So the first axiom is that for event E in sample space omega, probability of event E needs to satisfy the following 3 axioms. Okay? First of all, it's got to be between 0 and 1. And you'll hear me say that probability is a number between 0 and 1. That's key. So that's just this one. Probability is a number between 0 and 1. That's a nice way to think about it. Probability of big omega equals 1. So again, that is all of the events together. So big omega here, E is a subset. Then when you take the probability of the whole thing, you naturally get 1. And that gives us our notion of certainty. What's the probability that I roll a 1, 2, 3, 4, 5, or 6 on a fair 6-sided die? Well, it's 1. It's certain. I'm going to roll one of those. Okay, lastly, this is an intuitive one, but if we take our E and we break it into chunks, so I'm just going to draw a circle here for E again, and we're going to put it in chunks, so we'll just call that E1, we'll have an E2, we'll have an E3, and so on. Then, if you break it into chunks, then the probability of the union of all those E's, so that's separating them out, is simply the sum of the probability of each one individually. And so hopefully that makes intuitive sense looking at the diagram, but that's axiomatic. Okay, now with that we're going to move forward. Let's see. Okay, we get 4 probability results. Okay, the first one is sometimes referred to as the probability of the complement. So E superscript C is the complement, and I'm sure you're familiar with that. But if this is E here, then a complement, EC, is everything else. So it's all this space out here. Okay, and the sum of those two naturally must be 100% because that exhausts the whole thing. In other words, you could define big omega as E union E complement. That's it. And there's no overlapping elements either. Okay, great. Oh, here we go. Probability of omega is the probability of the union. And since they're mutually exclusive, we had our third axiom. Then we can add the two pieces. Great. Okay, number 2, E union F is this guy here. I'd like you to read the proof of that. For a diagram, it's simply E union F. So I bring the two together, but there's an overlapping region. And so if I just add the probability of the two circles, I double count the intersect. And so we're going to subtract it off one time. Okay, third, probability of the empty set is 0. Okay, so the empty set is sitting inside of big omega, and it has 0 elements. Okay, so I think that should intuitively be 0. Here's a nice little proof. So please read. And then number 4, if E is contained in F, then the probability of E is less than or equal to the probability of F. You will only get equality when the containment is actually equal. So when E equals F. Okay. Now let's do kind of a fun little problem here, just to practice some of these rules. The birthday problem, you may have heard this before. We've got a room with M students in our class. Remind me and we'll go ahead and do this in class. We may have 20 or something like this. What's the probability that at least 2 of the students have the same birthday? Key here is at least 2, so it doesn't matter if 3 have the same birthday or more likely 2 different birthday pairs. We're just looking at least 2. Okay? And that's what makes this a little bit tricky. If you try to set E as just 2 or more students with the same birthday, then you have multiple cases to worry about. Well, what about the case where there's 3 with the same birthday? And so on. The problem is just to find at least 2. Therefore, when you think about this for a little while, you'll realize it's easier to solve for the complement. Okay? So the complement is relatively easy to find. Now, how are we going to do it? Well, what we're going to do is we're going to do the number of ways for birthday. This is going back to our chapter 2 of counting, and we're going to have number ways to have different birthdays. Okay, so the number of the ways to have the birthday combinations is just 365 to the power m, and we're going to ignore leap years for this. But to make sure that they're different, then the first student could have 365 days for their birthday, but the second student can't have a match. The third student, this is going to be 363, and so on. Days are subtracted from the total. That's going to get me all the ways that we can have no matching birthdays. And so the answer that we want is 1 minus E complement. So we have a formula. Now, there's some R script given, and I'd like you to go ahead and type that in and run it, or you can just pull it down off of the website and copy it in and run it. And you'll notice that there's two ways to get that R script. This one is interesting in that it actually writes a function, and I don't know if we've talked about functions or not yet, but it uses the function and then this sapply command. So that's getting into a little more powerful functionality of R. Either way, we're going to get this nice table, and so we can see if there were 20 students in the class, then there's actually a 41% chance that we get at least one matching pair of birthdays, which is pretty amazing. Okay, next I'd like you to do this example here, relatively easy, and we'll go down to conditional probability. Okay, now with conditional probability, very interesting, very important. So I'd like to just sketch our diagram out here. Okay. Oh, I've got a little frowny face here. He says quite often one is interested in calculating probabilities when only partial information obtained from an experiment is available. That's true, but conditional probability is much, much larger than that. They occur all over the place. In fact, this is the first thing that's really going to separate your skills from virtually anyone else who has not studied probability like you're doing. Many things involve conditional probability. Okay, so again, we're going to be here, and let's just put in two circles. Okay, we'll put in E and F. Okay, now if I want to know what is the probability of F given E, what it means is event E is known to have occurred. So the sample space becomes E. It's limited now from the box down to the E circle. And so given that, what's the probability of F? Okay, so intuitively I want to build it up as follows here. So the probability of E given F is going to be, well, let's just count here and let's use our little n notation. We want to use its little n of E is in the denominator, and the numerator is going to be little n of E intersect F. That's this region here. Okay, so that chunk out of E, that's the correct probability. Good. Now I want to just put one twist on it, because that's in terms of counting, that's a legitimate way to find the answer, and you will use that sometimes. That's not the formula given here, and so if we just do one thing, n E intersect F, I'm going to go divided by n of big omega. Okay, we're fighting here. N of big omega all over n of E over n of big omega. And you'll notice the top here is the probability of E intersect F, and the denominator is the probability of E. These n of omegas cancel each other out. Okay, so that's where this formula comes from. Very, very useful. One corollary of this immediately is, we'll just put this on the side, probability of E intersect F is the probability of F intersect E times probability of E. I'm just multiplying across here. So that's very useful. Now, it's an exercise that will be in your homework set to verify this conditional probability satisfies the three axioms. So that's a nice one. Okay, we've got example 3.11, so I'd like you to work through that. It's relatively easy. When you do it, take note that you can solve it using the probability definition, and that's what they do. It may feel awkward. see if your intuition doesn't tell you this approach first, and just do it that way, and then notice the difference when they do it this way. Okay, so take note of that. Okay, now, let's see here. Same thing for this next example with the light bulbs, 3.12. Yeah, you can do that. So I'm going to go ahead and have you work through that one, and we're going to do one more thing here together. Law of total probability and Bayes' rule. So with this law of total probability, here's the scenario, and they write it out right here for us. You've got F1 through Fn, mutually exclusive and jointly exhaust the entire sample space. So you can think of it as the following, and this is a pretty commonly occurring scenario, maybe more than you might guess. So I've got F1, F2, F3, and so on, all the way up through Fn. Okay, now this is a little small. I want to go bigger here. So we're cutting this thing up, and the whole thing is F. So the whole thing is F, and I've got an event E here, which intersects with the F. Okay, and does it say anything about E? Okay, so for this event E, there may be empty for some of the F's. That could be. It's generally useful to just ignore those F's if it is, but that whole guy is E. So that's E. And now you'll notice that this here is E. Let's go finer. Fine point. This here is E intersect F1. This one, okay, we switch colors there. E intersect F2. E intersect F3. E intersect Fn. I've got all these intersections now. So hopefully it becomes manifest that if I want to find what's the probability of E alone, then the probability of E alone should be probability of E intersect F1 plus probability of E intersect F2 plus all the way up through probability of E intersect Fn. If I take all those mutually exclusive chunks, add them together, boom, that should do it. That's exactly this first line right here. Now, intersections, we don't have a natural result, but there's a corollary of conditional probability, and that is that the conditional probability is intersect divided by the probability of the whole part. In this case, f sub I is the whole part. That's the big box. And then I have this subset of it. And so this intersection is equal to the product here of the conditional times the whole. And that was the corollary that we just saw on our previous page that I wrote out right over here. So take note of that. And that gives us a result called the law of total probability.